演讲即将开始，请各位来宾尽速就座。
The lecture is about to begin. Please take your seats as soon as possible. Thank you.
欢迎各位来宾莅临创办人张建邦博士暨张江文资伉俪熊猫讲座。
Welcome, distinguished guests, to the Tamkang Clement and Carry Chair.
首先欢迎今天的与会来宾，世界和平基金会主席尤伟莫拉韦兹 （Uwe Morawitz） 及其助理 Mr. Jajang Wijaya。
First of all, welcome to today's guest, Uwe Morawitz, Chairman of the International Peace Foundation, and his assistant, Mr. Jajang Wijaya.
欢迎淡江大学许辉煌学术副校长，淡江大学精英会林建祥会长，淡江大学蔡志宏博士，淡江大学北美洲校友会联合会石宏珍副理事长，淡江大学潘博生研发长。欢迎理学院薛宏忠院长为我们介绍演讲嘉宾。
Welcome, Dean Hong Zhongxue of the College of Science, to introduce the speaker.
Thank you. Good afternoon, ladies and gentlemen, distinguished faculties and researchers, students, and our friends. My name is Hong Zhongxue. As a Dean of the College of Science at Tamkang University, it is my great honor to introduce our distinguished guest, Professor Gerard at Hooft. Professor Gerard at Hooft is a Dutch theoretical physicist and a Nobel Laureate. He is the international recognized as one of the most preeminent figures in modern particle theories. Professor at Hooft, he received so many important awards. I only just maybe give you some example. And Heinemann Prize in 1979, and Wolf Prize in 1981, and Lawrence Medals in 1986, and Franklin Medals in 1995. Of course, the Nobel Prize in Physics in 1999, and High Energy and Particle Physics Prize in 1999. And actually, there is one important award he just received recently. There's a Breakthrough Prize in Fundamental Physics in these years. In the early 1970s, together with his mentor, Martinus Weidmann, he developed the mathematical foundations that place particle physics on the firm theoretical footing work that becomes central to the Standard Model. For these landmark contributions, they were jointly awarded the 1999 Nobel Prize in Physics. More recently, Professor at Hooft, he received the 2025 Breakthrough Prize in Fundamental Physics, a so-called Oscar of the Science, in recognition of his profound contributions to gauge theory and the Standard Model. This modern accolade highlights the enduring influence of his work on the understanding of the universe. Beyond his groundbreaking research, Professor at Hooft, he has inspired generations of scientists and strongly advocate for international collaboration and education. Now, to celebrate his extraordinary achievements, let us take a few moments to enjoy a short video retrospective highlighting Professor at Hooft, Nobel and the breaking prize moments.
Theory. This year's laureates in physics, Gerardus and Martinus Weidmann, have made a decisive contribution to this language.
Professor at Hooft, Professor Weidmann.
On behalf of the Royal Academy of Sciences, I wish to congratulate you for your groundbreaking work. I now ask you to step forward to receive your Nobel Prizes from the hands of His Majesty the King.
And the standard model.
The special breakthrough prize in fundamental physics goes to Gerardus Hooft.
Well, the advice I want to give to new generations of scientists is that breakthroughs are still possible. There will be many of them in the future. And now, if the old folks say that they prove something, that something cannot be done, then my advice is don't believe them. Check it out yourself. But only use arguments that you fully understand. You will need courage. But that's what it takes to make breakthroughs. Tonight you've seen many examples where this attitude was really essential.
谢谢薛鸿忠院长，欢迎学术副校长许辉煌为我们致欢迎词。
Let us welcome Vice President for Academic Affairs, Huang to deliver the welcome remarks.
Esteemed guests, ladies and gentlemen, colleagues and students, good afternoon. It is my distinct honor and immense pleasure to welcome you all to the Tamkang Clement and Carey Chair Lecture. We are privileged today to host our truly distinguished speaker, Professor Gerardus Hooft, a giant in the field of theoretical physics, and a Professor Emeritus at Utrecht University, the Netherlands. Professor Hooft is globally celebrated for his profound contributions to our understanding of the universe, notably for which he received the 1999 Nobel Prize in Physics for elucidating the quantum structure of electron-weak interactions. His work has fundamentally reshaped modern physics. Today, we eagerly anticipate his lecture on the timely and vital topic, education and collaboration in fundamental science as bridges between nations. This lecture holds special significance as it is part of the TAIWAN BRIDGES program, a magnificent initiative organized by the International Peace Foundation and 12 academic institutions, including Tamkang University. Over the course of this program, 31 Nobel laureates will share their knowledge and wisdom across Taiwan. And we are profoundly honored that Professor Hooft is the second laureate to grace our campus. I would like to specifically thank Mr. Uwe Moravec, chairman of the IPF, for the tireless dedication in making this program a reality. The presence of a speaker of Professor Hooft's caliber perfectly embodies the spirit of Tamkang Clement and Carey Chair Lecture Series. This series was established through the generous endowment fund created by our visionary founder, Dr. Wen-Chang, and his beloved wife, Mrs. Carey Chung. for the express purpose of advancing academic excellence at this university. This series is also affectionately known as the Panda Lecture Series. Dr. Chung chose the panda as a symbol because it represents reality, spirit, loving, and determination, the very qualities we seek to foster in the academic community. Later, the Panda Trophy will be presented to Professor Hooft in recognition of his extraordinary academic achievements and contributions to humanity. Professor Hooft, we are deeply grateful for you taking the time out of your tremendously busy schedule and making the long journey from the Netherlands to Taiwan. Your commitment to sharing your insights is very inspiring. To all our esteemed guests and participants, thank you for being here. I now invite you to join me in officially welcoming Professor Gerardus Hooft.
谢谢学术副校长。现在让我们用最热烈的掌声欢迎今天的讲者 Professor at Hooft.
Let's give a warm round of applause to our speaker, Professor Gerardus at Hooft.
Well, what can I say? I am very honored to be here with such a marvelous introduction. I'm also pleased to see that this entire hall is completely occupied. So I hope this interaction will be successful. International collaboration is particularly important in the very advanced and modern sciences. An important example of these sciences is physics, and the physics of the elementary particles in particular. And an example of collaboration is CERN. CERN is an international, or actually a European laboratory which has 24 member states of countries in Europe. And besides that, there are there's one observer state, the USA, and there's 3 associated states and 7 associated member states. So practically covering the entire globe. Scientists from all over the place love it to come to Geneva and to discuss with the other scientists they meet up there the questions that are bothering us in physics. And as soon as you enter the CERN laboratory, nationalities, religions, and examples of distinction between countries all disappear. Within the confines of CERN, you discuss science only. And science means the problems that you are encountering in studying the fundamental building blocks of nature. On this map, this is the, what you now see is the example of one of the main detectors inside these tunnels. This detector is here just, they started building it, it's still mostly empty. The whole thing will completely be filled with electronics to study what happens when particles hit against each other with tremendous forces, and you have to understand what these forces do when particles hit each other. Which direction do they fly? How do their properties change, and so on. CERN actually is built on the border between Switzerland and France. If you look at this map, you see two big circles. The smaller ones of these is actually now still the biggest laboratory of this nature in the entire world. It's called the LHC, the Large Hadron Collider. And in this collider, the collider had shown its importance very firmly when it was discovered that in our collection of particles, elementary particles, that in our view constitute all the possible forms of matter, there was still one particle missing, the Higgs particle. That particle was being searched and found by the Large Hadron Collider, the small little circle that you see in there. I don't know whether, yes, I can. And this small circle is a Large Hadron Collider. The bigger circle is something that may perhaps be one day constructed in the future. That will be an international super particle collider, which has a diameter which is 4 times as large as a Large Hadron Collider. The Large Hadron Collider had a total length of 26 kilometers. The big collider, which may or may not be built in the near future, has a circumference of 100 kilometers. These particles that it contains are circulating around in both directions in this big circle, 3,000 times per second. 3,000 times per second, they pass through the border between France and Switzerland 4 times without caring anything about customs controls or whatever. They go through the circles peacefully, they go through the borders peacefully, and they should bring us new science as yet unknown. The main thing that I want to talk about today is the collaboration that is needed to make such a particle, such a gigantic machine with gigantic demands to make it run properly. Thousands of people are all working on the same experiments at CERN and are needed to get the whole thing under control and to build this fantastic accelerator that is supposed to make new discoveries about the universe. We have seen that the smaller circle is very successful. Who knows what a larger machine gives? Well, there are some doubts among the theoretical physicists whether at all this machine will discover anything. We don't know, but one day perhaps it will be discovered what the uses of such a machine and what new knowledge it will bring to science. So collaboration has been absolutely beneficial in the mutual understanding, such as the understanding is also conducive for peace and collaboration. So I'm going to talk about collaboration and peace, which is the main subject of this organization, bridges for peace and understanding in the entire world. But there are many fundamental questions in science that we are studying that are being studied by other nations in other laboratories. And many of these places do not have the scientific background that is needed for such a project, and therefore it is very important that they try to do that anyway. It is important for a peaceful coexistence of all its inhabitants. So many global problems such as war, poverty, availability of resources such as food, water, energy, and provision of health may be addressed by realizing full scientific collaborations of all nations. So how do you do that? In one go, I want to discuss major fundamental topics in modern science, and I want to discuss the topics needed to establish peace and progress in the poor countries. We want to have both, and we think these two different questions are very strongly related. So progress in scientific thinking can then only come about when different people from different places come together. They investigate different mysteries, and they follow different approaches to stumble upon solutions. Some scientists spend their entire lives hiking through the difficult terrain of constructing ingenious detectors and exotic events to see how the world looks like. But other investigators build gigantic machines to see whether they understand this experimentally, and ingenious detectors such as large telescopes. With these large telescopes you want to see what the rest of the universe is like, and how the rest of the universe is also controlled by the same scientific insights that control what happens on the planet Earth itself. And then still other investigators, like me, are more interested in the theoretical description of all these things that happen. They do the calculations. The calculations are very complicated, but the most striking discovery of science in the last 50 or so years is that these laws of physics are extremely accurately valid. So what you see here is a series of diagrams that once, when we are investigating these questions, my supervisor Veldman and myself, we were investigating, and we encountered all these diagrams. These diagrams all mean something scientifically and enabled us to express the laws of physics in a very precise way. Precision turned out to be the secret key to further progress. So indeed, some investigators work with meticulous accuracy to check their ideas and understand their progress, but others are extremely sloppy, and they may have some wild imaginations of what might happen. The strange thing and the beautiful thing about our science is that all these people are necessary to help us solve our problems. Being together to solve scientific problems then is the key way to also bring different people from different nations in contact with one another, and to have them all study the same processes. Not only people from different nations are different, but also people themselves, one by one, differ from one another. Our world is so vast and complex that many of these different approaches for its investigation can be justified, and there's place for many serious attempts to improve our understanding. There are a few things, however, that all these scientific researchers have in common. And that is that every one of these researchers has to build on the findings of others. of their colleagues. So science is a collective exercise. Only by being open and by using the openness of other scientists, one can contribute to this scientific adventure in a meaningful way. Because of the differences, there's trade among nations, and there's discussion between people. And such differences can lead to progress taking place. The most elementary feature of nature's laws, often underestimated at this level, at the most basic level, is that they are exact, as I said. History of science is littered by discoveries, new discoveries, that have been possible only when people had learned how to be very precise in doing the calculations and in checking what works and what does not work. And what is needed to ask the questions that have been answered now, but have been mysteries for a very long time. So there is such a thing as a standard model of the elementary particles, but that didn't emerge before it was realized that the different laws people have been studying all work together in one grandiose scheme called the standard model. And I want, no, sorry, I'll go back. How do I move back? Oh, here it is. What I want to describe is the elementary particles being that fit in a very precise scheme, obeying all the laws of nature that we know in fundamental science and that we have checked to be true to a very high degree of accuracy. And there were, however, still problems left. And the problems which I'll briefly mention now was the problems for which ultimately by solving them we won a Nobel Prize. And that is that when you try to compute how different particles interact, what happens when one particle hits another particle with tremendous force, what happens among these particles? And the answer is given that if you try to calculate their interaction, you find the interaction to be infinitely strong. Now, what does it mean that two particles interact infinitely strongly? What you then are saying is, I don't understand anything about what happens. So when you get infinity as an answer, the real reason for getting that answer is that you haven't understood something. And that we realized when we started these calculations. If you do them in a stupid way, you just follow the laws that you thought were exactly valid, you got things that at first sight didn't seem to make sense at all. So only by when all these people that worked together, we found the answers, how to do this precisely. And the answer was lying hidden in all these diagrams that you see on this picture. These diagrams together, each of these diagrams was describing an infinitely strong interaction, but some interacted infinitely strong in that way, some in that way, and if you add them all together, the net result was a finite interaction that you could calculate. And what was found is that if you calculate these precisely enough, and you are not being deterred by infinity as a temporary answer, only then you can understand what it is that makes these particles tick, that makes them behave the way they are seen to be behaving. When you analyze the detectors, so these big detectors were there to find out what comes out when two particles hit, well, they come out going in all directions in a very complicated way, but eventually with such a probability they do this, with another probability they do that, and these answers together all gave finite numbers that where we could check theory with experiment. So that turned out to be the correct way to proceed from this point on. Many people think that now physics is over. Now we have all the particles, we know how they interact, what else is there to be done? Well, we found that there are many questions that still can be asked, of which the answers known today are not accurately formulated. So we don't know exactly how to do this the way we should be doing to get the finite answers all the way for every particle under all circumstances. No, theoretically, we can imagine circumstances where particles interact with so much force that also these calculations that we gave today are still not correct. They still hide infinities in them. There's still something wrong. We have to do this better. So we were then, in the very end, plagued by questions of this sort. And what they really wanted to know is, science is showing us the way, yes, but how can we collect this science, and how can we do all these measurements and determinations and calculations more accurately than ever done before? And yes, it can be done more accurately, but you need much, much more force. So now you can ask, suppose that a poor developing country also wants to get some of the fun of making discoveries, of finding out how these particles behave. What can you recommend to them? Well, one's mind then wanders in different directions. What would be the wise thing to advocate to poor developing countries? And the answer is, well, that you think will be, well, take problems that are of direct importance to them. So I think that you can ask these countries to do investigations in the topic of environmental science, of how new animals, some animals get extinct and some other living creatures get a better position in the new world caused by pollution and differences and changes in the field. You can ask them how to make better products cheaper and more efficiently so that a growing population can still be fed. You want this good, same growing population to control the delivery of water, of energy, of food, of health issues, and so on. So those, you would think, should be the scientific questions studied by the poor people. However, in general, it would be wrong to say that they should only study these sciences. In fact, although they have obvious direct applications, but in the Western world, if the Western world would have done such a thing, if all of Europe would have only investigated things that are necessary for them without asking the questions, why and how did God make these things work? Why are planets moving around in ellipses around the sun? What are the laws? If we did not answer such questions, we could perhaps today, instead of finding our world as modernized as now, you would still be discussing how to make better candles for light. How can you put more colors in the flame of a candle or something like that? But we would never have discovered electricity. You would never have found that there are much more efficient way to generate light than by using candles. So this is the kind of questions that should be answered, should be discussed, and should be answered. So the poorest countries should feel no constraint in buying the newest high-tech weaponry. So that already happens now. But even if a country is very poor, they buy very expensive drones or machines of this century to defend their country. Should they be doing that is a thing you can ask. And at first sight, it seems that would be unwise to recommend them to try to invest in such technologies. But then, I think that would again be a wrong argument. And one of the first people who saw this was Abdus Salam. Abdus Salam was one of the few Nobel Prize winners who came from a developing country. He was born in a country that only after he was born there was called Pakistan. Before that, I think it was part of India or so. Not well defined. I don't know exactly. He didn't know where he was born, in Pakistan or India. But he said, now it's Pakistan. And he said, the correct answer is no again. You should let these people not only make fancy weapons with modern science, you should let them do modern science all by themselves. Only that way you can introduce them into the world of the 21st century and beyond. So instead of putting making a constraint in what they buy by constructing new weaponry in the Western world, they should go to countries like Switzerland and France and go to CERN and participate in the art of making new, shocking discoveries, not about how making good weapons, but about finding out how the universe runs, what the forces are that make the universe behave the way it actually does. Salam therefore did what he thought was best for his country. That is to erect a new physics laboratory called the International Institute of Physics. And that originally was given a different name, which is, where am I now? No. Yes, the institute he created was called ICPT, International Center for Theoretical Physics, and that was in Trieste, in the north of Italy. That's an international institute which does the most modern research in fundamental science. The activities there, in that sense, were adopted to foster advanced studies and research, especially in the developing countries, but not only in the developing countries. There should be very strong interactions between an institute like that and the world institutes such as CERN, and similar institutes in the United States and in other well-developed countries. It didn't stop with the ICPT, which is now called the Abdus Salam Center of Physics. And what happened a couple of years after that was that other institutions of the same type were being set up in other parts of the developing part of the world, such as there was an institute like this in Sao Paulo, in Brazil, in Kigali, in Rwanda, and in Beijing, China, which at that moment was still something like a developing country. But China quickly picked up a better position in the race towards progress and science, as you all know very well. Later, a different institute was being founded in Natal in Brazil. So you see that if you look at the conference room in such an institute, you see it looks very modern. It doesn't look like the Third World War, which is trying to find out how to make chicken lay heavier eggs or something like that. No, here fundamental science is being discussed. In fact, I want to go to a short sideline. I want to raise a question which has been asked to me several times. And the question is, the Netherlands is a very small country. at the turn of the previous turn of the century, around 1900, there were about 5 million inhabitants in the Netherlands. And now it's something like 16 million people living there. But these are still very small numbers compared to the number of people living in China, in Brazil, or wherever. So the question was, how come that there were so many Nobel Prizes won by people who contained so few inhabitants at all? So there were Van het Hof, Lorentz, Zeeman, Van der Waals, Kamerlingh-Onnes, and a couple of other people who won Nobel Prizes. This, I just wrote down here, the first 8 of them, which was all got a prize before 1939, so, or 1936. So how come that our country did so well in these days? And the answer is a very simple answer. There was just one smart person who realized that our school system was not optimal in the past. That person was called Rudolf Thorbecke, and Thorbecke was a statesman in the 18th century who said that in our schools only youngsters with wealthy parents are allowed to study topics such as rhetorics or philosophy or Bible, religion. That kind of things are being studied in the schools, but they knew absolutely nothing about modern technology, about strange languages, and so on. That should change. And so he advised our politicians in our country to establish a new school system called the higher civilian schools, HBS in Dutch. And in those schools, all youngsters should go who want to learn more than what they learn in their primary school years. And the topics that they should teach were at least 4 languages. Besides our own language, Dutch, they should also learn French and English and German. That's because these people will have to do commerce. They'll meet people who don't speak their own language. They have to learn these foreign languages. And the same thing about science. They should not only learn rhetorics and philosophy, but also topics such as physics, mathematics, biology, chemistry, and similar subjects. Those subjects should be taught at the high schools. And when these schools came, immediately they attracted the interest of many new youngsters. Around the last turn of the century, around 1900, the school was, or a little before that, the school was very attractive for young people. And young people who went there are exactly the ones which I had on this previous slide. All these people had followed the higher civilian school, and they had a very efficient education. So this explains why, for instance, Lorentz, who is in one of these pictures, yes, the second one is Hendrik Lorentz. He was chairman of the Solvay conferences, well-known conferences where modern science was being discussed. And I think he was that because he spoke all these 4 languages. So we could talk to Einstein in German, to Maxwell in English, and to Poincaré in French, and Van der Waals in Dutch, of course. So they had an enormous advantage compared to scientists from other countries. This advantage was used to earn Nobel Prizes. It was about that simple. I'm skipping a few intermediate steps, of course. They had to be very, very clever themselves as well, but they had an enormous advantageous position to earn new prizes. So in this aspect now, when I talk about India and China, it will be different than a talk I gave of the same spirit a few decades ago. Now these countries are no longer developing countries. You can't really call them that. They now, there's no reason now to criticize those countries for having chosen the wrong thing to do when studying modern science. Instead of studying science of economy and health and the science of making big weapons, they made the science needed to send, yes, this, by the way, this was Tarbecker, and the science, this is standard model, I'll come back to it later, the science which enabled the Chinese to put a moon lander on the backside of the moon, which is quite an accomplishment. Even if you're a developed nations, it's very difficult technically to do such a thing. I still remember from China in the old days when I first visited, they were making their first particle detector. It had, for instance, a magnet weighing many tons, but the magnet was moved manually using pulleys. Now it would be almost unthinkable that these heavy magnets would be moved around by using just manpower, but that is what they did. And it brought them into modern science after all. So the ICTP focuses on developing nations, but at the same time, it does produce top science. And that's the main contents of this talk, that from doing relatively low-level science, we very quickly go to the top. And the ICTP is playing an important role in international science. It are the best of all scientists today in the entire world have been in that institute just to discuss what can be, what we are working on, and how elementary particles fit in schemes such as the standard model. But in the meantime, when I just looked recently at one of these programs that they were discussing, one of the programs was called a workshop on machine learning. Now, machine learning, I think you all know what that really means. It means making devices that can become intelligent, like humans, yet built out of electronic components and nothing else. Artificial intelligence. So now artificial intelligence is going to be a major source of science, which 20 years ago was hardly thinkable. So it's actually one of the most hot topics in modern science. And one of the major questions being asked today is, will we ever be able to make a machine that is more intelligent in all respects than a human? And such a machine should be given a name that I will call SHAI. AI stands for artificial intelligence. SH stands for superhuman. Can one ever make a device that is more intelligent than a human being? Most scientists today say, nah, that will never be possible. Just like they said a few centuries ago that, you will never be able to discuss the fundamental particles in the universe. They say it with the same disdain that this will not be possible. In fact, what most people are now counting on is that maybe we have to use quantum computers. And they're all dancing the same dance, making us believe that quantum mechanics will be the answer to this question. I don't believe that. I believe you need very good and fast calculations, but whether quantum mechanics will be the only way to do those calculations, I have my doubts, because I'm asking the next question. What is the special thing about quantum mechanics that is explainable in terms of ordinary logic? And then you find that there's no difference between quantum mechanics and ordinary classical mechanics. So I have some doubts that whether you actually need quantum mechanics to make this next step. I think you need this. You need to use your own common sense and your own intelligence to make this next step. And well, I will talk a little bit about that now. So there are many reasons to be very afraid of this development. So what will research into artificial intelligence bring to humanity? And many of these developments could be unexpected, unwanted, negative, and dangerous or even catastrophic when they are being applied at large scales. So I think indeed that it's the task of modern scientists to warn the public that yes, there are dangers of this sort that are inherent in such new, totally new and difficult to foresee procedures in scientific thinking. So of course we have to think about the safety of our planet all itself. But the fear is that there's no way of stopping this kind of investigation right now. People are doing it, and I think they will be successful. So in my intuition, this superhuman artificial intelligence is entirely possible, but you have to understand that there are clearly some problems that you haven't understood how to solve and how to control. But if they become very intelligent, they might also become very wise. So my counter-argument is, make sure they are not only intelligent, but that they only use wisdom, and they won't kill all the people on this planet. There's no good use for that whatsoever. Make them all want to do the same thing. Stop the wars, stop the deadly competition between nations, but start to collaborate and do more science. Learn how beautiful this universe is, and that artificial intelligence, no matter how cleverly done, could bring us lots of good. And I'll argue why I think that. So it's the whole question is that artificial intelligence has to be studied by and produced by humans, which are not as intelligent as the devices themselves. So isn't there a conflict there? I think no, science has never produced such a conflict. So I don't think there is a conflict of that sort. But what you have to know is what human intelligence means. And that it turns out to be a very difficult question. I'd like to try here the suspicion I have is that the reason why this is so difficult is that humans, being human, are not being honest. They tell lies to each other. They particularly lies to their enemies, but even tell lies to their friends. They even tell lies to themselves. So it's a very complicated kind of intelligence, and the intelligent devices that we really want don't need these properties. They don't ever need to lie. So, but that makes them unhuman in some abstract but very useful way. So not human artificial intelligence, but superhuman. So we cross that border and we see what lies beyond. And I think what lies beyond is real intelligence and fortunate consequences of the use of intelligence. So not intelligent devices, but also intelligent ways to use these devices. And so thinking machines will have to understand themselves also on what laws human intelligence actually is based. So why does the human mind lie? Why do we do it? For very good reasons. It's the way we live. Our aim is not to become more healthy just ourselves. Our aim is just to continue the formation of new life. That's what biology tells us. Let us use the logic of biology, the logic of living creatures, the logic that you find that you hope to disentangle, and the logic of the way humans think. Let's put all that together. Then you get a sort of super combination of understanding and science and intelligence that would outperform everything humans can do. So just imagine what would it be if our country would be governed by someone or something that is 1,000 times as intelligent as humans. I think that could only bring prosperity. We see that modern leaders are doing stupid things all the time, and it should be, there should be better answers than that to make our world work. So now a few afterthoughts, which is that there is, of course, opposition, not only against intelligent designs, artificial intelligence, but also opposition against the scientific method in general. And you see it in very different ways, and you will find out, for instance, that religions are often at a rather bad equilibrium with scientific findings, and the question is, why does that happen? What can we do about it? Well, in the Western world, the religious objection against most of the scientific findings have subdued sufficiently to make things work. But in some countries, religion is still the prime system that produces laws for people to behave, whereas intelligence beyond religion is often not used. You find that those religions are still objecting certain features of science, which most scientists find as being facts that cannot be, need not be further disputed. For instance, the theory of evolution, biological evolution, it contradicts standard religious beliefs in various ways. First, evolution theory sheds a very different light on the origin of mankind and its relation to animals. That's scientifically practically a fact. We find thousands of indications this is so. We shouldn't try to resist against these findings, yet many religions do. Evolution theory claims to cover vastly longer time spans than most of the holy books. They say that the world has been created a few thousand years ago. No way. The world has created a few billion years ago, which is much more than that. And so, so these findings are also in contradiction with what their religions find. And eventually there are other things, for instance, the size and the age of the universe also don't fit well. The age of the universe is also in the order of billions of years. So, and the size of the universe is of the order of billions of light years, much, much bigger than everything religions ever talk about. Also, life itself may be very sparse. Maybe there exists no planet at all where life formed the way it happened on Earth. That is not yet excluded. So, most scientists think that there will many planets will harbor life. Even there will be many planets which harbor intelligent life. I have my doubts here. If there were places with intelligent life, there would be some places with intelligent life a billion years ago. Those would have evolved into what? Into something that you would know about, I think. Anyway, these differences are still have to be worked upon, both at the level of religion, but also at the level of science. How can we understand what is going on in this universe, and how can we make this all fit together in one picture that we want to maintain? The opposition to modern science is also found in a different form. I'll very briefly mention that, and that is there are what we call crackpots, mavericks, people who dismiss all the modern science and try to replace that by their own ideas. Of course, that is allowed. You are free to challenge modern science in terms of the ideas you have just developed yourself in some short moments and think that you can replace that. But mostly these people have not studied science hard enough. They haven't really found out what the modern textbook have given. And the arguments used in modern science, why something works this way and not that way. We know it very precisely, and the odds against one single person finding the right way where thousands of others have failed, that is very unlikely. Perhaps not uncommon, but I'll say it's very unlikely. And one mythical figure in that respect is Albert Einstein. Einstein was thought to be the most intelligent scientist in the world, so ever, and that statement is found in many history books of science, and that inspires young people to skip studying of science the modern way, but just try to do it the way Einstein did, by thinking very hard while you're asleep, and then you wake up with the answer in your mind. Perhaps you wake up with an answer, but you wake up usually with the wrong answers. So what these people are missing is self-control and self-criticism. That's very important, but it's also important for the modern sciences and for the highly developed sciences to be critical. Whenever you find a scientific finding, either by yourself or by collaborating with many others, there may be a mistake in your finding, and you should be the first to find it. You shouldn't wait until others tell you what the mistake is in your thinking. And that is a very healthy discipline. I found myself, I make many mistakes when I investigate something, but usually I'm the first to find my own mistakes myself before others do. Not always, and then I'm very embarrassed that someone found an error in my paper. But that person will be my friend, he will not be my enemy. Because he read my paper, he found a shortcoming in it, and that happened once or twice. And I'm very happy that people study my own work that way, and I'm not getting very upset the way that people do who think they can reinvent science all by themselves. So my conclusion is that we need good education. We need education from the very beginning when you're sitting in the nursery school until you enter university. Everyone needs education. The higher the level the education is, the more strongly you make the competition in these institutions. The more enthusiastic you can make the students follow these institutions, the more successful you will be, and not only you, but also the country you're in will be successful and reach new heights if people find what they want to know about in their education. It's not easy because some people are not interested in science, but they're interested in the subject that they're inspired to when they see their parents watch television. The parents watch television and shout to all the soccer players that they should make a goal. But the little kid sees when his parents are like that, says, I want to become a soccer player myself. Well, we don't want 11 billion soccer players in this world. We need them, yes, because they give us all fun things to look at, but not that many. So watch out before your children want to become soccer players. There will be too much competition, and that's not good for us either. So yes, I hope to bring forward some ideas that are raised when you ask questions about collaboration of science, science being bridges that connect different continents and countries in such a way that the results can only be peaceful. Thank you very much.
Okay, thanks, Professor at Hooft, for so inspiring talk. Before we start the Q&A session, just let us have a few seconds to set up the seats, and we can sit down here. And can we just? They were just at the chair. Okay. Yes. Also, now we start the Q&A sessions. Anyone or friends or students will be welcome to give the questions or comments. Or
here.
Yes. Yes.
Good afternoon, Professor Hooft. Thank you for that inspiring speech. So I am a PhD student here in Taiwan. So over here to your left, yes. So I'm a PhD student here in Taiwan, and I originally come from the Philippines. So I was inspired by the idea that scientific collaborations can serve as bridges between nations. And my question is, what advice would you give to young scientists who want to contribute to global scientific collaborations?
Well, that is very hard to tell in general, because as I said in my talk, people are different. So you are different from the person sitting next to you in all sorts of ways, and the advice to be given to you will differ from the advice to be given to the person sitting next to you, let alone everybody in this hall. So a general advice is impossible. I think my general advice is try to be an expert in something. Try to dive into one of the numerous problems that humanity is coping with. It can be science indeed, but it can also be art. It can be music. It can be that you want to become a soccer player, actually, or you might want to do something else. You want to be a chess master. All these choices are open. You must make your choice at some point and ask around. If you have made a choice, I want to be a specialist in this or that, ask someone who is a specialist in that subject, what does that person feel, and how did that person became successful in that field. I can assure you, maybe Albert Einstein was very intelligent, maybe Richard Feynman was a very intelligent physicist. I'm not a very intelligent physicist. I'm just very average thinking power, but I have certain principles that I follow very strictly when I'm doing science. I try to learn from my mistakes. Whenever I make a mistake, I won't say that mistake I don't want to do again. And of course you must love your subject. So yes, check where you think you might be different from other people. Then for many people who don't really aim that high, you don't have to at all. For instance, my children happen to be experts in something else where they can earn a decent living, so it's fine, but you're not yet world famous. You don't have to be that. But if you want to, well, that means that you have to invest as much as you can in the topic you want to specialize in. And again, what that is, I don't know. For physics, the question is indeed very hard, because physics is going to change. If artificial intelligence comes off the floor and becomes really intelligent, it can take over the job of a physicist and say, by just thinking, I can figure out how to answer all your questions. I hope that won't happen too soon, but that could in principle happen. It could be that physics gets stuck, that the only questions you can ask are the questions which we cannot answer, because they are too difficult. The machinery that should be needed to answer the question doesn't exist, and so on. So there's a danger if you go into physics that you might see the end of it, and you would rather choose a subject of which you don't see clearly an end, like the subject of art or music or whatever. So that's ultimately it's going to be your own choice, and it's going to be the subject that you really want to study, and whether it's science or whatever.
Thank you for that answer.
Great. All right. Does any other questions? Yes, please.
Thank you for your wonderful speech. I am from India, and here I am a postdoctoral student in physics. So my question is, normal people who follows religion practice from childhood, and how could we teach them scientific, the normal life in scientific way, means understand life in scientific way. I mean, scientific mind is very important. How could we teach them? And mean, we science people, what step we should take?
I couldn't follow everything you said from it, so maybe you can summarize what your question is. Of course, you want to be a scientist. Or
Normal people who don't do science in their daily life. So for scientific, I think we should make science very easy way to reach them. For scientific mind.
There's something with the acoustics here that makes it very difficult for me to hear.
Can you just slow down a little bit? Yeah.
Am I audible now?
Yeah.
How to make people believe in the scientific way, is that it?
I mean,
by giving endlessly many answers to different questions. Science is the art of answering questions that you would be tempted to give the wrong answer. For instance, why do you get sick? The easy answer is because you've done something bad in the past. You've been a naughty girl and you got sick for that reason. That's what the religions say. But we say, scientists say, no, that's not why you became sick. You may have become sick because you have been drinking the wrong kind of water somewhere, or there may be an inflammation in your body. We can find out what caused you, not only how to recover from your sickness, but also what causes it. What was the reason? Why did you become sick? Why is someone else not sick? The person sitting next to you is totally healthy. Why are you sick? And you have to search in your past what the reason is, but that will take a long time. So what you can do much better is look up in the books. Then you find there are thousands of people who are just as sick as you are now, and science discovered that such and such is the answer. This is the cause of that sickness, and this is what you have to do to avoid getting it, or to cure from it. And I mentioned sickness as an example. I didn't mean to say that you are sick, but whenever you have a question such as that, you find that the old answers are no longer correct. There are better answers. The science tells you that most of the answers to very commonplace questions can be made much better than what you would naively believe. And it will help you enormously if you follow that line.
thank you very much.
Okay, thank you. Any questions? Yes, please.
Thank you very much, Dr. Hooft. My name is Rosa Ye. Work as a chemical engineer from Chicago. I work in the medical device company, and currently I'm working in the AI development. So I would like to ask Dr. Hooft, as we all know, recently the quantum computing becomes more and more popular and attract a lot of people's attention by using in the AI technology. So from your perspective, what aspect of quantum mechanics can be used in the AI technology to accelerate the AI development? Thank you.
I'm not sure I understood your question exactly. There's quantum physics as opposed to classical physics. But as a scientist, I don't quite understand the boundary line there, and I don't believe there is a boundary line. That all of classical physics can be explained in terms of quantum mechanics, but the converse is also true. All of quantum mechanics can be explained in terms of a classical procedure, but that part of the story you don't hear so often, and most people don't believe it. I claim that I can give many examples of this is true, such a way that I am suspecting that the truth is absolute, that quantum physics follows from certain classical things happening in agreement with classical logic at the ultra short scale. The problem with that idea is that what happens at the ultra short scale happens at the really short distance scale, a distance scale which is billions and billions of times shorter, smaller than where we can do physics. And we can try to do physics in that domain, but we cannot do any experiment. So there's this enormous gap that makes us believe that quantum mechanics is the ultimate story, and we can't jump over that gap to see that there are other ways to explain what quantum mechanics really is. This is my belief. It's not based on solid science alone, but also a little bit on intuition, that there should be something underneath quantum mechanics. It shouldn't be a primary, but should be a secondary feature that makes particles behave this way when they collide. And I know enough about colliding particles to suspect that there's something like this going on. Only I wish I could give you a better answer than that, because it's now still very dubious. So I listen to my friends who find more and more miracles lying in quantum mechanics. And whenever I see these miracles, I say, no, if you look more carefully, you see it's not a miracle at all. There's no breakdown of logic at all if you think that there are classical degrees of freedom that generate quantum behavior, even at the largest scale. That they already know. We know that classical behavior of charge carriers in a conductor can become superconducting because of quantum mechanics, and then miraculous things happen, but it's not against logic. So, so quite generally speaking, I think there are ways to understand that quantum mechanics and classical mechanics may be the same side of one coin after all.
Right, thank you. So since we have so many activity later, so we can take one more last question, short questions. Right. Probably we will leave it to tonight. You want to go? Okay. Maybe the high school activity. Yeah, you can. Thanks, Lloyd.
Yes.
我用中文啊。你好，我是淡江高中的教务主任。
OK。
那的发展处主任，非常谢谢。 让我们的孩子能够透过这个机会，能够接触到很多的物理学的常识。在这边呢，我们想要请教博士，就是说，在目前的整个的量子力学的发展，特别是在量子纠缠方面，对于说我们未来的宗教信仰上面，会不会产生一个很大的冲击？
Sorry, I translate his question for you, and actually he just want to know the progress on the quantum mechanics development, and also especially the quantum entanglement, the knowledge of the quantum entanglement will affect on the religions of the people because they coming from the high school, they are just Christian, right? You just淡江是天主教还是搞 Christian? Yes, they are Christian Christian high school, so they want to know any kind of new development of the quantum mechanics, especially the quantum entanglement, will that affect the religion itself? Yes.
Well, I have to give sort of the same answer as I gave to the previous question. In a sense, it's the same question, what distinguishes quantum mechanics from classical physics. Now, there is this enormous gap that I think there is a classical explanation of what's going on, but that classical explanation involves processes taking place in a way which is totally invisible to us. We cannot do experiments, we cannot do observations, so we cannot check this. Only in our minds we can. If we are smart enough, we will find out that how to jump over that gap. But today is not known. So I can't give the answer to that question because I don't know the answer. It's as simple as that. But I know only in some simple examples I could find that even though you might think they can produce entangled states, in fact you're not producing entangled states at all. You're just producing states which show a very complicated probability distribution. Now, very complicated, this is just a short answer I'm going to give now, just to give you an idea that you should be able to follow, is that entangled particles just describe a situation where the probability distribution is very complicated. It not only involves these particles, it also involves all the other particles around them in such a way that you can say we cannot possibly understand how these probability distributions could come about unless we use the word as entanglement. But I think that is a way of like giving up to answer a really difficult question, but finding the easy question. The easy question is that quantum mechanics is something else. It shows a phenomenon, entanglement, that we can't explain any other way, therefore quantum mechanics exists. That's a short argument. To me, it's a little bit too short, the argument, because I can make simple examples where entanglement does seem to exist without anything taking its place. So that, yes, you can find models where entanglement itself can be explained also classically. But the problem is that you can only let that explanation work for you, do something useful like a quantum calculation, if you understand all these extra variables that we don't understand today. So there's something very elementary missing in our understanding. That doesn't mean our understanding is wrong. It means there's something missing. And what is missing is to find a better answer as to what happens when particles are in a state that we call entangled. But in reality, the entanglement is caused by a wrong description of its probability distributions.
Right, sorry. Due to the limited time, so I have to stop the Q&A sessions. So let's thanks Professor Hooft again for his wonderful speech. Thank you.
现在有请学术副校长为我们颁证淡江大学熊猫纪念讲座。
We now invite the Vice President for Academic Affairs to present the Tamkang University Commemorative Award.
谢谢学术副校长。现在进行纪念手模仪式及签名仪式。
Now we will proceed with the handprints and signature ceremony.
我需要乖乖，我需要乖乖跟奖品。
我们会送他，而且是台积电纪念版。你要吗？我有，可以给你。我有很多。
你先问乖乖。Yeah.
我订了一些。
Hello. Let me explain what's this one for 乖乖. Yes. 乖乖 is one of Taiwan's most iconic snack brands. So it was introduced in 1968 by 乖乖 Food Company. Although it began simple as the corn puffy snack, it gradually evolved into the unique cultural symbol in Taiwan. So, for example, like a TV advertisements promote the slogan like 乖乖 make kids behave. 乖乖让小孩子变得更乖。 So the name Guai Guai naturally means the be good, behave. Originally, the impress that children who eat this one will become the obedient. Okay, the snake fiber such as the coconut, this one is a green color, and the cinnamon, the coconut is yellow color, and also the 5 species, the red color. So around the early 2000s, almost 25 years ago, a unique and humanist cultural practice emerged. So right now, all the engineers in Taiwan begin press the green Guai Guai packet on servers, the machine, even the lab equipment. Why is very important for our Taiwan culture? Because the green one, the symbolize the normal operation, like a green static light. And the yellow and the red symbolize the warning or the arrows, the message. So we don't like the yellow and red. So the second name also means the be good. So impress the machine will behave and not the manufacturers. So this becomes a very widespread tradition among the IT engineer, scientists, and research, and also the university library, data center, and the chip fiber. So Guai Guai starts as a child's corn snake, but it now emerged into the unique cultural symbols associated with the reliability, good luck, and engineering humans in Taiwan. So it makes it's a distinguished part of Taiwanese scientists and also technologists. That's our history for this Guai Guai. So we also prepare this one for our high school students, and this one is for you. You can have the Guai Guai and also some special your name card here. Yeah. Yeah. Want to ask you to sign your name and the dates and all those.
Where? With what pen?
Yeah, and sign here.
什么？越南说什么？越南说什么？
Full printer like this ones. Yeah, and those. Full printer.
Q&A 是院长跟主任都要主持。压不下去吗？上次尾田也很用力。
Thank you, Professor Gerardus at Hooft. Please be seated.
对，他在查手书，等我一下。现在进行大合照，请各位与会来宾看向前方镜头。
We will now take a group photo. May all guests please look toward the camera.
请把桌面上的杂物先清空，然后把麦克风压低，谢谢。 感谢各位来宾参加淡江大学熊猫讲座，今天的演讲到此圆满结束。
Thank you all for your participation. Today's speech has now come to a successful conclusion.
请要合照的高中生至台前。
哎，同学，丹江的同学对不对？丹江的同学在第二层，赶快上来第二层，下面留一排就好，快点，我们时间有限，待会就没时间给你们。OK，be careful， gentle 一下好不好？年轻人，赶快 ，No， go down now，go down。 百灵高中的同学，等一下，第2场是你们百灵高中的同学。等一下，先组织好，先下来组织好，快点快点，时间有限。百灵高中的同学准备好。好，单向同学都有了，单向同学快点快点，我们拍完就要走了，我们就团体拍照1张而已。百灵高中的同学先等一下，先不要进来，你太，赶快进去，赶快进去，赶快进，快点快点，你们先走，你们先走，你们先走。丹江的赶快快点，最后3秒钟，不等你们哦，快点，丹江的同学赶快过来，丹江同学，你再不来我们就要关了，我们要换另外学校了，快点。OK， 可以来拍吧。OK， 谢谢我们丹江同学，丹江同学请离开，赶快离开，请不要签名，请不要拍照。丹江同学请离开，现在请离开。百灵的同学，我们来吧。校长领队，百灵的校长赶快。丹江同学请离开，请离开，请离开 ，right now， 请离开 ，go away，go 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 away。The second one， they are so lively. Yeah, yeah, we have a second. 百灵高中的同学，快点！百灵高中的同学还没有的，赶快来拍。百灵高中的同学，来，前面的同学全部蹲下，前面的同学蹲下。百灵的都到了吗？百灵，百灵，快点！赶快自己找位置，没有的在前面拍，前面蹲下，快点。拍照喽！静心，那个王老师，王老师，静心的，快点，快点，快点，快点，快点！静心的同学，快点，准备好，准备好在那个 stage 过去那边，赶快准备开始了。OK， 谢谢，谢谢百灵的同学。还有一个，做一个 ，the last one， 静心的老师，王老师，来吧。百灵的同学可以请离开，拜托，百灵的同学，我们离开，往下一个移动。百灵同学，我们离开了，我们离开了，快点离开了，离开，快点，你们。
同学出去了，然后一群同学出去，又现在又跑进来。
我们没有时间，后面没有时间，还有第2场。
好。
哎，接教官，静心的老师，快点，就你们在静心那里，在进修。来，同学来，同学前面的同学给他蹲下，前面的同学第1排蹲下，快点。长官他们，谢谢。OK， 同学，我们还有下一个，来王老师，我们把他带走，谢谢。下去喽，你们先到物理那边去喽。OK， 谢谢同学，我们走了，快点，赶快走，我们到下一场去。final one。